record. I'm going to do this, and I'm going to go to lecture array, and I was talking about feature sizes, close.
So what do you mean on that slide by what are the 5 features? Because the only feature that I really understood from the reading was this feature size per se.
Yeah. Okay, so the 5 things that count as a feature. So let's do my Zoom thingy again. I'm recording. And that means I got to move Ben out of the way. Ben, move over.
All right, I'll change seats.
Okay. What we've got here, I need my pen, is I've got a word line. And the word line width is a feature. I can only make the word line the minimum feature size. So it's got to be at least 1 feature wide. And like for a particular process, a feature may be 10 nanometers. But if I scale this process down, which I'm continually doing, I'm going from 10 nanometers to 8 nanometers. I don't want to have to change all my calculations. So it's kind of like a program where you put a variable up at the top, a global variable, which is F. And I say F is 10 nanometers today. And then I can change it tomorrow to 8 nanometers, and it will automatically scale everything down.
Automatically.
Yes. Okay. So
that phrase since like the early 2000s.
So this is why. The number of features is important, and that will scale down as the process scales down. Well, I need this contact. I need the drain, the source, and the contact for the capacitor over here, and I need half a feature for a space between that and the next one to give it room so I don't short the capacitors out every time. Over in this direction, I need a half a feature for the digit line contact because the digit line is shared between 2 cells. So it only counts for half. So when I add that all up, I get 1, 2, 3. 3F is the length in that direction, where F is a number like 10 nanometers or so. Going in the other direction, I've got the active area of the transistor right here. And that active area, the minimum width for that is going to be 1 feature. And I also need a space between that and the next active area. So that's a half a feature because the other half of a feature counts in the other cell. And the same thing on this side is a space. So in this direction, I have 2F. So the area of 1 cell is going to be 6F squared. 6 times 10 nanometers squared, or whatever it is that day. Okay, now what else was the point of this slide? Okay, so if I can get a process that I can build smaller transistors in, then I can get my memory array in a smaller area. Okay, and the word line width and the spaces and the contacts and the active area width are all the things that count as features. Now everybody move to the other side of the room. Now the defect we've already talked about on this open array architecture is that this comparator here, the sense amp, is comparing VCC over 2 plus signal, where signal may have a positive or a negative value. It's comparing that to VCC over 2 from a different part of the array. So this VCC over 2 may not equal that VCC over 2. Aren't you glad to know that? Okay. If I do something like this with a folded architecture, instead of comparing the digit line from array part 1 to array part 2, I'm comparing from one row to the next row. That next row is really close to the row above it, like nanometers away, and it's in the same, and they're running parallel to each other. So the likelihood of them picking up the same crap is very high. This has a much higher signal to noise ratio. High SNR. The only thing that changed, well, there's a couple things that changed, is where I'm comparing it to across there. Now, one thing that's that's an advantage you don't see here is this sense amp has to fit in whatever the distance between the two columns are. It needs to fit in the column pitch. This sense amp needs to fit in a 2-column pitch. And if I flip it over and do every other sense amp on the other side of the array, this can fit in a 4-column pitch. So I've got a lot more room to lay out that sense amp with a folded architecture. The rows are running along the word line driver. Yeah, up and down, and the columns are running side to side. So the primary reason for the folded is you get a better SMR. And we'll see in a few slides that this is 6F squared, but this one here, the folded, is 8F squared.
Yeah, since it's like 25% bigger, but that is that is the trade-off of since it has a superior signal noise ratio, is it worth it for it to be 25% bigger?
Yes, folded one for a while.
Fair enough.
And then came bi-level plaid. Just because they needed a silly name for this. Okay, yeah, and I'm behind. This is where I was supposed to start today.
My fault.
No, it's not your fault. I'm behind every semester like this. I just define it as behind. Okay. So the cells I've got, if you draw for the transistor diagram from that layout, with the open architecture, you have the common digit line contact going into a transistor, going into a capacitor, and they don't show where the capacitor is connected. The word lines coming down here, and that looks like this. The folded, I'm losing more space too because I'm alternating. I'm putting one row, the one column, I'm going on odd spacing, and the other one I'm going on even spacing. So I'm kind of like mishmashing them together too, which is another reason why it's making it bigger. Yeah, this is what the layout for the folded digit line looks like. And let's zoom in. And everybody lean to the other side of the room. Okay, what we've got here is we've got one feature size for the capacitor. I've got one feature size for the word line. I've got a half a feature for the digit line contact. I open this up, and as I open it up, going around that, it gives room for the capacitor on the next one, so I can squeeze those together a little bit. But the whole length here, and then I've got the other one in another space. This is 4F, this is 2F. So now I'm at 8F squared. Significantly, no!
Are you frozen again?
Okay, Tell me not to get so excited when I come back. Yeah, just one more. Okay, because when I get excited and I touch the screen too much, this is when it happens. Calm down.
Too much excitement is not allowed.
Oh, come on.